Loud. Okay, I think we've got everything. So where do we want to start?
For 21.
Okay.
Can you start with 2021, please?
Sure.
Can you explain or go over 21? I know it seemed to be easy, but it is a little bit confusing for me.
Okay. So first of all, we all understand that the vertical line means given, correct?
Yes.
Okay. So when we're trying to describe in words T1 given W, that's basically saying that if we choose somebody at random, right, what's the probability, or this is the event that the donor is going to have type O blood given that they're Caucasian or white, right? That's what the W stands for.
So basically what I did with the probability of blood type O happens given the race is white.
Yes, exactly.
Given the race is white, okay.
That's it. Yep. It's just in English, it's the event that a donor has blood type O given that they're white. Exactly. And then to compute that probability, we look up here
Yeah.
and we see that we're only looking at the white donors, right? So our total is just going to be these four percentages added together.
80.2, I guess that's what I have.
Exactly. And then
36.
obviously the good
Yeah.
is 36. So it's going to be 36 over that 80 and then
Yeah.
reduce, and that's your answer.
Okay.
Now, as far as W and T1 being independent, this is something that people struggle with a lot. They think of mutually exclusive when they're trying to figure out independence. And so that's a very common mistake to think that two things are, have to be mutually exclusive in order to be independent. And that's not at all what independence means. Independence just means that one doesn't influence the other. So if these two things are independent, then that means the probability of a random donor having type O blood would be the same if you chose from the entire population versus if you chose from just the white population. If they were independent, being white would not have any bearing on whether or not your blood type was 0. So what that means is if you're given that extra piece of information that that the patient or the person is Caucasian, it's not going to change the likelihood of them having type O blood. So basically, mathematically, what it means is you would have to calculate the probability of them having type O blood, given that they're white, which we just did in part B, and it comes out to right around 45%. And then you would have to calculate just the probability of a random person having type O blood. So that would be add all four of these, right? 36 plus 7 plus 1.7 plus 1.5, and then put that over the total, which I assume these all add up to 100. And that ends up being a little bit over 46%. So they're not exactly the same. So therefore, those two things, those two events, being Caucasian and having type O blood, are not independent. Now, as far as mutually exclusive is concerned, that just means, is there such a thing as an overlap? Can you be both things at the same time? And of course we can. We can see there are 36% of the population is both white with type O blood. So there is an intersection, and it doesn't equal 0. So therefore they're not mutually exclusive. So that's how we would tackle 21. Okay, and then I'm sorry, but Yo, you had asked for 61, 51?
Yeah, before we go there, so for B, 36 over 80.2 would be the answer. Do we need further than that, or that's it? 36 over 80.2.
I'd like you to then reduce it to, a decimal with at least, I like to see at least 4 decimal places of accuracy, but, give me at least 2 or 3.
Okay.
Because whenever we answer probability questions, we always answer them as a decimal. Because if you told somebody, if you just went to some schmuck on the street and said, hey, the answer is 0.36 over 0.802, they'd be like, okay, I have no idea what that is. Right? They have no concept of that number in their head. If you told them the answer is 0.45, they'd go, oh, 45%, right? They would understand that. So you want to relay it in a number that makes sense.
Okay. So the next question is, he said, when it's independent, one does not influence the other.
Correct.
But in real experiment, I've thought that independent variables, the dependent variable is affected by the independent.
Yeah, and that's where the words independent and dependent, unfortunately, are overused in statistics because they can kind of mean 2 different things. So when we're talking about 2 different variables and whether or not they are independent of each other, it has nothing to do with the vernacular or the naming of saying this is an independent variable and this is a dependent variable. That's why we normally call them explanatory and response variables to get away from that independent dependent, so there's no confusion. So, and independent dependent is usually only reserved for true experiments where you can really manipulate the independent and see if it has a change in the dependent, like trying to see whether or not blood pressure medication works. You have a double-blinded trial where people are on, different dosages of this medication. So therefore you have control over the independent variable being the medication, and then you're measuring their blood pressure, the dependent variable. And that you would call them independent dependent in that situation because that's an actual experiment where it's double blinded and you've got your placebos and your and your control group and all that kind of stuff, and you're manipulating a variable on these people, i.e. giving them different dosages and seeing if there's an actual measurable difference. Then you would technically call those independent dependent. But in the vast majority of statistics where we're just looking at data and we don't actually have control over things, we just call them explanatory and response. And then it also helps to not get it confused with the idea of 2 variables being independent. And when we talk about 2 variables being independent, it has nothing to do with the independent-dependent thing. It's all about one influencing the other or not.
Okay.
Which, kind of comes back to it because, like you said, the independent variable influences the dependent variable. So if 2 variables are independent, then they don't influence each other. It's kind of counterintuitive. Yeah, it's kind of crappy that the word's used twice.
Okay, making sense. So for the 423, I don't know if it's really that easy, but or I am missing something. For A, for example, what is the probability that a random selected government employee having an advanced college degree would accept a promotion? So I have like 276 over 920. I added let me see. So both for this professional, I added those, like the 184 plus 276 plus 460 is 920.
Okay, so the probability that a randomly selected government employee having an advanced college degree would accept a promotion.
So 276.
How many, which one of these things represent a government employee having an advanced college degree?
I believe to say that both spouses said professional, the professionals. Both spouses professional.
So it should be 276.
276, yeah, over 920.
And where'd you get 920?
460. I mean, over 460. I forgot. Yeah, 460.
Okay.
Yeah, over the total. I mean, accepted. Over the total is 460.
276 divided by 460. That is not the correct answer.
That's not, okay.
Dr. McBride, I think we have in the given, it says every single one of those employees has an advanced college degree. So our total is 1,000.
Right.
So
And
it's,
so this is the problem with probability, is that the questions can get confusing when you use English and not symbols, right? Because you try to figure out what exactly are they asking. Well, as we just heard, that if you read the whole thing, we've got 1,000 government employees who have an advanced college degree, right? So all 1,000 employees have an advanced degree. These numbers up here represent whether or not their spouse does, right? Whether or not their spouse is professional or not, right? It really has nothing to do with anything other than that. So when they say, what is the probability that a randomly selected government employee having an advanced degree, i.e. just pick somebody from this entire pool of 1,000, would accept a promotion, that's literally just 743 over 1,000, and the answer is just 0.743. It's that simple.
okay, I see. So that makes sense now.
Yeah, it's just the problem is that the when you have English sentences, it's really easy to misunderstand or misinterpret what the question is actually stating.
Okay, that's easier. So says B will be 257 over 1,000 then.
Exactly.
Yeah.
And the C is going to be 370 over 1,000, correct?
No.
Random selected government person minimum college degree has a spouse with a profession. Okay.
I put the 370 on C.
Basically 460.
It's going to be 460.
Yeah.
Oh, 46. Okay. All right.
Which one are we talking about? I'm following along. We're on 420.
So on part C, again, it's where the wording gets really confusing. In this table, when they talk about both spouse being professional,
Yes.
that's their idea of having an advanced college degree. So this column here where it says one spouse is professional, this represents U.S. government employees who have an advanced college degree and their spouses do not. This column here represents their spouses having an advanced college degree or blah, 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 being professional, because it says both spouses are professional. It's a terrible table because up here they call it having an advanced college degree, and in the table they call it being professional. It's terrible. So when it says the probability that a government employee having an advanced college degree has a spouse with a professional position, we're really looking at this total here of 460. Because in order for their spouse to have a professional position, it has to be in the both category, because they're already assuming that the advanced college degree ones all are considered professional. It's terrible. They should have labeled these differently, but that's part C. The answer is just 460 over 1,000 because of.
Okay.
They're basically they're equating being a professional and having an advanced college degree as being the same thing.
Okay.
Yeah, it's really bad.
Okay.
So, lesson to be learned here, folks, is when you're putting in tables, label them better. Because this is really poorly labeled. It's very confusing to the reader.
Words are important.
Yes, they are. Okay, are we good on 26?
No.
Okay.
Can you go over 2026?
Sure.
Okay.
So you have to pay attention to what all these things mean, and I think oftentimes, at least for my puny little pea brain, it helps if I kind of label things. So for instance, we're gonna, oh, I didn't want that. I wanted a highlighter. Highlighter. Nope, come on. Highlight. Well, damn it. Okay, so we'll color code them so we can kind of see what they are. And this one will be blue. Okay. So now an employee works at the high capacity level. Well, we can all see that that's just the last row, right?
Mm-hmm.
So come on, give me my pen colors. Maybe try over here. There we go. Let's do highlighter and let's do yellow. And finally, I got my act together. Okay. And then an employee falls into the highest, right, extensive formal training category. So that's this last column, right? Not row, but column. So these are that category. And then an employee has little or no formal training and works below high capacity, right? So they can't be in high, they work in either low or medium, and they have little or no formal training, so little or none. So that means that the blue category is little or none
Mm-hmm.
and works below high capacity. So now we can visually see what these three things are. And now it should be very easy to do part A, because probability of A is simply just add up all the yellows, right? Part B, add up all the greens. Part C, add up all the blues, okay? Probability of A given B. So it's the probability of being yellow given that we're in the green. So if we're in the green category, what's the probability that we're yellow? Well, the only yellow that's in the green category is 0.22. So this answer would be 0.22 over, what is that, 0.36. And then you'd have to reduce that, because that's what given means. It means within that subset. So we're only looking within the subset of B's, because that's our given. Within that subset, what's the probability that we're an A, right? That we're in an A group. So this one says we're in the subset of not B, right? Because B with a line over it is the complement of B. So we're everything outside of the green. So within that subset, what's the probability of being in the green?
There's not. No.
Yeah, isn't that impossible?
Yeah.
So it's basically saying, what's the probability of being an employee who falls into the highest extensive formal training category, because that's B, given that we are not an employee who falls into the highest formal, so it's impossible, because how can we, be something when we're already given that we're the opposite? It's like saying, what's the probability of voting yes, given that we voted no, right?
Yeah.
So
Watch.
this one, we're now saying, what's the probability that we're not in the B? So what's the probability that we are not shaded green? So we're looking at everything that isn't this last column, right? This is all the stuff that's not shaded green. So what's the probability that we're, one of these things, given that we're in C? So C says we're here. Well, inside of C, right? So this is now our new total. Our new total is just blue, because the given becomes our new total. So if the new total is blue, we basically know that the person we chose at random, like we chose somebody at random, we showed their employment record to somebody else, and they said, okay, I'm going to give you a hint. This person that you chose at random, I can tell you that they have little or no formal training, and they work below high capacity. And you're like, okay, so I know this person is in group C. So I know this person is in one of these four categories, because that's all of group C. Now, amongst all of those four categories, which one of those, right, one or ones, satisfies not being in B. That becomes our good, right? C is our total, and our good is not inside B. Well, aren't they all not inside B?
Yes.
So what would the answer be?
All of them in the.
Right, it would be all of them over all of them, and the answer would be 1.
Oh my goodness.
Does that make sense, Amy Sue?
No, it doesn't. I thought I had it there, but okay. So this, and I'm so thankful for whoever brought this question up. So in this situation, it's the probability of not being in B given that you are C. Is that
correct?
Like,
Yep.
I mean, we're really trying to think about what we're trying to get to.
That's exactly it.
Probability of not being a B.
Yep.
But in the C category.
Right. So not being a B is all of this, right? This is everything that isn't B.
Yes. So
but we're given that we're in C. So because we're given C, we only look at this. This becomes our new total. That's our total. And remember, probability, right, is always good over total.
And so that total is the, well, what, I mean, I could look at my answer. I could just add them right. It's like 0.14, right?
Let's see.
Yeah,
3,
11, 12, 13,
8, 14. Yep, 0.14. You got it.
Okay. But now you're saying
within that new total, which one of those is good, i.e. satisfies the rule of not being in the green category?
okay.
And all of them are.
Okay.
So let's look at A given B again to remind ourselves of why this works the way it works, right? If we're given B, so we'll do this in a different color. Do it in red. So if we're going to do this one, then B is our new subtotal, right? That's our new total that we're concerned about. So this is our new total.
Yeah.
Because we know that what we have comes from this category. Within this category, which ones are in A, right? Which ones are the good? Well, these are the only ones that are the good.
Okay.
And so we get 0.22 over 0.36. But in the case of the third one, we get all of it over all of it, and we're good to go.
Okay.
It's kind of like saying, what's the probability that you're a mammal given that you're a human being?
Okay.
You know what I'm saying? They're one and the same.
Yeah. Okay. Okay. So to this, and you know, this is about where I am, you know, so far. And so like for this week, I'm not as far ahead as I was hoping to be at this point. But so, you know, up to this point, I was finding my experience like, okay, you know, I'm going to do all this by hand, you know, and I'm the one that's been doing everything by Excel. So it's like, you know, I don't even really see the need up to this point to start using Excel. But
no, not at all, not in this homework.
Yeah, and I think the gist that I'm getting is, and that was just my question, is even for the remainder of the homework, I don't think it makes sense to go out. I mean, because I've become a quick study, or I've been trying to be a quick study on Excel, and, you know, I've been, you know, somewhat successful in finding that. But I mean, is this whole homework, most of this homework, going to be like
by hand?
By hand?
Yes.
Okay.
Yeah, the vast majority of it. There's only a couple questions where you would want to use maybe even just a calculator. You wouldn't even need SAS or Excel for this one.
Okay. Okay, thank you.
Yep.
Before you finish at 2026, can you go over C? What about C?
Okay, well, A union B just says take all of A and B and put them together. So take all of the yellow stuff and all of the green stuff and add it together just make sure you don't count anything twice, right? So it's just 0.1 plus 0.15 plus 0.16 plus 0.22 plus 0.1 plus 0.04. Just add those 6 numbers together, and that's A union B.
Okay.
And then what about A intersects C? That says,
0.22, it will be 0.22, the intersection, right?
well, be careful. It's A intersects C,
Okay,
not
C.
A intersect B. Yeah.
Yeah. Okay.
You're correct that if it was A intersect B, it would be 0.22. But what's A intersect C?
So basically the yellow
No,
No.
and the
it
blue.
should be 0.
It'd be
Yeah.
0. Yeah,
Zero,
because remember the
yeah.
intersection is what they have in common. It's their
Yes.
overlap. And there
Yeah.
is no overlap between those two groups.
No, yeah.
What about B intersect C?
The same. And,
Yes,
Yeah.
because there's no overlap between the green and the blue as well.
Yeah.
All right, are we good with all those?
Yes.
Okay,
Thank you.
yeah, of course. Okay, do we have questions on 441?
Could you go over C on 41?
Of course. Now, first and foremost, I want to make sure that everybody recognizes what kind of probability distribution is 441, discrete or continuous?
What was the question?
Is
Sorry.
441 discrete or continuous for a probability distribution?
Continuous.
Good
Measured.
guess.
Yeah, measured. Is that measured? Let me see. If it's measured, it's continuous. If it's counted, it would be discrete. So
Right. Do you count the number of calls or do you measure the number of calls?
no, you count.
Yes. So
You
it
count. So
is.
it's discrete. It's
Very
discrete.
good. These are discrete. Okay. So part C, suppose a call center must notify a supervisor if a customer recalls the center more than 4 times within a week. Well, more than 4, right, would be just 5 and 6, because that's what more than 4 means.
Yes.
So what proportion of customers who contact the call center will require a supervisor is simply just these two numbers added together. So 0.035, 3.5%.
All right. That makes sense.
Okay, so are we good on 441?
Yeah. So
I have a question. Sorry,
No apologies necessary. Go for it.
when you asked the question about is it the probability, is it continuous or discrete?
Mm-hmm.
My brain went straight to the decimal points, but then you said, do you count the number of calls or do you? So can you go over that distinction one more time?
Yeah. So a discrete probability distribution is one in which, and we don't look at probabilities because probabilities always have decimals. We look at the values associated with the random variable. And here the random variable, i.e. the thing that we can change from day to day, is the number of recalls. And that random variable can either be a continuous random variable or a discrete random variable. A discrete random variable is something that is counted, and a continuous random variable is something that is measured. Like you measure your height and your weight and your age and things like that. But you count the number of siblings, the number of times you go to the movies in a month, the number of bathrooms in your home, or in this case, the number of recalls in one day or in 1 week, whatever this is. I think this is quality. They call it within a week. So the number of times a customer called the center back within a week of his or her initial call. So this random variable represents how many times a given customer will call back within 7 days of their initial call. So about 15% of them are satisfied with their tech support and they don't call back at all. 23% have to call back once within that week, right? 35% have to call back twice, and so on and so forth. So the random variable, the y here, is the number of calls, or sorry, the number of recalls, and those are counted. So therefore, this is a discrete random variable, and therefore
Great.
is a discrete probability distribution.
Great. If I may tie this into the final project,
Yes.
the question about the continuous data set. So that's the same idea, or not, is continuous. Yeah, that's what it was asking.
Yeah, so continuous data set would be a variable that is measured and not counted. So for that final project, when it asks you to come up with a variable, you know, that would have a continuous probability distribution, then you need to come up with a variable that is a continuous variable, and a continuous variable is simply something that is measured. So you just have to make sure that you are coming up with a variable that is measured and not counted. And remember, a variable is simply an answer to like a survey question, right? You know, so the number of recalls is just the answer to the question, how many times does this person call back within a week? Well, I asked how many times, so I'm asking you to count, right? If the variable is your height, then I'm asking you to measure your height, and that is a continuous measurement. It's a continuous random variable because you measure your height. Now, even though if you did actually put that on a survey, every single person who answered would round their answer to the nearest inch, so the data would look discrete because there wouldn't be any decimals, right? Your answer would all be, you know, if you put everything in inches, it would all be, you know, so 6 feet, 3 inches would be 75 inches, right? Or even if you did it in centimeters, if you were, you know, anywhere else but our country type of thing, people would still, report their height to the nearest whole number, but that is still a continuous variable, because if you actually went and measured their height and got as accurate as you could, you would have decimals on all those measurements. You know, nobody is exactly 75 inches tall. So it's that kind of thing. So, and the same thing if you ask them for their age, you know, age is a measurement of time. So even though everybody would report 23 years, 27 years, 42 years, 57 years, whatever they happen to be, nobody's going to say, well, I'm 45 years, 6 months, 2 weeks, 3 days, and 5 hours, and so many, you know, nobody's going to break it down, but it is a measurement of time. So age is considered a continuous random variable. Height is a continuous random variable. Weight is a continuous random variable. Those types of things. So yeah, so when you're trying to come up with something to fit that scenario for the final project, you just need to make sure that you're coming up with a variable that is measured and not counted.
Thank you. That was very helpful.
My pleasure. Okay, are we good on 41? Or I should say, any more questions on 41?
So on 41, for A, did we go over A? I have like 0.67 plus 0.21 plus 0.014.
Correct, because if you're more than 3, you would just add up 4, 5, and 6. Exactly.
And then do we have to divide it by the total, right?
Well, you don't divide by the total. These are already probabilities, so you just add them up.
We just add them up.
The only time you divide by the total is when you are given numbers, right? In this table here, we were given numbers and a total. In this table, we were given probabilities, so we just added up those, and those were our answers. Same thing here. These are probabilities, so you just add them up.
Okay, cool.
Yeah, and just be careful, right? You just got to make sure that you read the questions properly, because when they say at least 2 times but less than 5, well, at least 2 but less than 5 would just be those 3. Right? Because if you're less than 5, you have to stop at 4, and if you're at least 2, you include 2.
At least 2. Okay. Okay.
So it really comes down to an English test, understanding what at least 2 means and less than 5, right? And more than 3 means, as you said, 4, 5, and 6.
Mm.
That's why math symbols are so much better. You know, it'd be so much easier if they just said 2 is less than or equal to y, right?
Yeah.
Is less than 5. Then you'd go, oh, okay, well, that I can figure out. That's 2 to 4.
Mm.
But isn't this also the same thing as saying, you know, 2 is less than or equal to y is less than or equal to 4?
Mm.
Right? You can do, when you have a discrete random variable, you can write an answer a lot of different ways, because being less than or equal to 4 is the same thing as being strictly less than 5, because there's nothing in between these two, right? There's a total gap. When it's a continuous random variable, those two things are totally different. So being less than 5 or less than or equal to 4, those are totally different, because there is actual stuff in between 4 and 5. But with discrete ones, there is not.
Yes.
Okay?
All right. Thank you.
All right. How about 46? So any questions with 46?
Can you go over A for us?
Yeah, absolutely.
How to get the 20?
So first of all, we need to recognize that this question here is a binomial distribution. And we know it's a binomial because the probabilities are constant and the trials are independent. And everything is either a success or not, right? So when you say all 20 return products have some type of problem, that means, okay, so N is 20, that's my sample size. My number of successes is 20 because all 20 of them are going to have some type of problem. And now I just have to figure out what's the probability of having some type of problem. Well, 5% are defective. That's a problem. 45 are defective but can be repairable. That's also a problem. 35 have small surface scratches but are functioning properly. That's still a problem. And 15% have no problem. So those are the only ones that don't have a problem. So my probability of having some type of problem is 85%. So if we stick this into the binomial formula, we'll get the correct answer. But you know, the binomial formula is easy when you're doing all that are exactly the same. Either, you know, they all have something or none of them have something. So what's going to happen is you're going to get 20 choose 20, which just equals 1, and then times 0.85 to the 20th. Because that's the binomial formula, is that you calculate the number of ways you can do it, which is 20 choose 20, and then times the probability of excess raised the number of excesses, and then technically you do times the probability of a failure, which I think is 15, raised to how many failures we have, but in this case we have 0 failures, and we know anything raised to 0 is just 1. And as Cheryl wrote, you can do it very easily with the formula, right? The PDF formula with the binomial, right? I'm not going to write the whole thing out, you know it, binomial, and then it's going to be n, comma, 0.85, comma, 20. And if you run that in SAS, it'll give you the right answer. So this is one of the few homework questions where you're going to want to use some sort of technology. You can do it in SAS with the formulas that I provided with you guys. They're all in the how-to summary right down here. Here's all your week 4 formulas, right? And once you put them in SAS, it's just a matter of changing the numbers to the right thing. So in this case, we want to know the probability, right, of n being 20 success being 85 and our number of successes being 20. And if we run this, there's our answer. Now you can do it in Excel just as easily because Excel has the Binom PDF formula in there. You can do it in a graphing calculator very easily. It just depends on, you know, which technology you want to use. Or at least in the case of this one, it's such a simple calculation that you could literally just do 0.85 and raise it to the 20th in your calculator and get an answer, and that's fine. But, you know, to do the rest, you're going to want to use technology for the rest. Because to do part B, you have to do 20 choose 6, because we have 6 successes out of 20, times, okay, probably exactly 6 of our products are defective and not repairable. Well, defective and not repairable is 5%. So that's 0.05, because that's our p-value, right? Raised to the 6th times 0.95, the opposite, right? The complement, raised to the rest of them, which is 14. And you would have to do that by hand, or very easily in technology, our success was 5%, and we wanted exactly 6 out of 20 successes. And if we run this one, oh, that's a CDF, sorry, I need to be up here. Six out of 20, exactly 6 out of 20. So we have to do the PDF, not the CDF. And we run this one, and there's our answer for that one. And the rest are pretty much done the same way. We just have to see, of the 20 return products, 6 or more are defective. Okay, so now we have to use the CDF function. But just like before, when they say 6 or more, then we're looking at, you know, 6 through 20 being defective. Defective and not functioning, which for probability's sake, our P is going to equal, well, defective and not functioning properly. Well, if they're defective and not functioning properly, couldn't that be defective and not repairable, or defective but repairable? Doesn't it mean both of those put together? So our P should be 0.5 in that case. Now we just have to run the correct programs. But if we want 6 or more, we would either have to go back here and run this PDF function 15 times, run it as a 6, then a 7, then an 8, then a 9, then a 10, all the way up to 20, and add all those together, big fat pain in the ass. We don't want to do that. Or instead, we use the CDF version. And what the CDF function does is it adds up all those probabilities for us, but it starts with 0 and goes up to the value that we stop at. And since we want 6 or more, that doesn't work because this one starts at 0. So we have to be smart about it and go, okay, so I'm going to go up to 5. So it's going to go 0 through 5. And there's my probability of 50%. Now, if I run this, this is going to be the probability. Yep,
Dr.
go ahead.
Wouldn't you do 1 minus in
Well,
probability?
when I'm done, yes. So
Well,
I
when
would
you're
run.
done, wouldn't just add it in the whole thing.
Sorry?
You wouldn't just add 1 minus in probability.
Oh, I don't know if you can do that and if it gives you the
can.
right thing. Can you?
I did it, yeah.
Oh,
1
sweet.
minus. Yep.
Oh, nice. Because I was always doing that afterwards with a calculator. Oh, look at that. Learn something new every day. Nice job. Thanks, Cheryl.
Sure.
Yeah, so we have to calculate the complement of it, so we have to do 1 minus it to get the stuff that we're looking for. And then the last part, the last question, is back to one of those absolutes where it says none of the return products has any sort of defect. So yeah, so basically all of them are basically defective free, right? None of them has any sort of defects. It's the same thing as saying all 20 of them are free of defects. So you can think of it as all 20 of them with a p-value of 15, or you could think of it as 0 of them with a p-value of 0.85. It's going to be the exact same thing, but basically it ends up being the complement of A. It's just 1 minus what you got in A. Well, not really. Sorry, I take that back. It's the complement of the probability of A. So instead of 0.85 raised to the 20th, it's really 0.15 raised to the 20th. And when you do 0.15 raised to the 20th, you're going to get a really, really small number. Terribly small. Let's see if sometimes it won't even give it to you. So let's do all 20 of them. All 20 of them are good. Yeah, and see how it gives it to you with the E?
Yeah.
So that's scientific notation. So that means your answer is basically 0. You've got, 16 is point. It's a decimal point with 16 zeros and then 3. So it's basically 0. Okay, so any questions on 46?
So what would be the answer for D?
D should be 0. I mean, it's technically 0.15 raised to the 20th, but when you run it in technology, it's so small that it's equivalent to 0. It's that number. And that number is so tiny that it's the same thing as basically 0.
Okay.
And can you run SAS for C?
Let's see. Of the 20. Yeah, we just did that one. Of the 20, 6 or more are defective. So in order to do that in SAS, you have to do the complement. So what we did is you have to do 1 minus.
Oh, okay. Okay.
So the CDF function adds everything up from 0. So this part right here takes 0 up through M. So in this case, when you set M to be 5, it takes the probability of 0 successes plus 1 success plus 2 plus 3 plus 4 plus 5. It adds all those probabilities together. C wanted to know the probability of 6 or more. So if we take the probabilities 0 through 5 and subtract them from 1, that gives us the complement, which is 6 and above. So that's why we had to put this 1 minus in here to get the complement. And so when you run this one, that's how you get the 97.93%.
Oh, okay. All right. I see. Thank you.
Yep. Okay. 5-1. The last question, where we go into the Poisson, or you can just call it Poison if your French isn't great. And
French is my first language. So.
There you go. So you can pronounce it even better than I can, because my terrible English tongue doesn't pronounce it well.
Yeah.
So this one, the first part, what is the probability that the firm will have more than 5 sales in a randomly selected day? Well, it's just a binomial, right? This is just a regular binomial distribution, because we have independent things, independent, each sale is independent of the next. It doesn't matter if the first person buys or the second person buys. So all of your sales, the probability of a sale remains constant, right? There are two basic main things that you have to have in order for something to qualify as a binomial distribution. You have to have that the trials are independent and that the probability of a success remains the same. So in the context of this question, the trials, and if you could see me, I'm putting air quotes around the word trials. Trials being independent means that the internet hits are independent, meaning whether or not people come to the site is completely independent as whether or not somebody else came to the site, right? So those are all independent, and the probability of a sale remains constant, because according to this, they tell us that we're supposed to assume that they have 2,500 hits per day, and the firm estimates that they get 1 out of 1,000 hits results in a sale. So there's your, your probability that stays constant. 1 out of 1,000 is your probability. 0.001 stays constant. So yes, it's a binomial. So part A, when it asks for what's the probability the firm will have more than 5 sales, well, we have to, plug the numbers into the formula. In this case, our sample size, right, our N is 2,500 because we have 2,500 hits. And our P, our probability, is 0.001, right? Because that's the 1 out of 1,000 as a decimal. That's the probability of a success. And here, the firm wants to know the probability that they will have more than 5. So basically, it's going to be 1 minus the PDF, right? The summing up formula of 5. Because the PDF of 5 will add up 0 through 5, and then more than 5 sales will be the 1 minus it. So we're going to do the same thing we did with part C, only now with slightly different numbers. Well, not slightly different, hugely different, right? Because now our sample size is 2,500. Our probability is 0.001. We still want to add up the first 5 and then take 1 minus that because we want to have more than 5 sales. So if we do this one, there's our answer for part A. Part B, I already told you, we already discussed it, right? Part B says what are the conditions that are necessary, right, must be satisfied in order for us to make the calculations in part A, i.e. the conditions that make this a binomial. Well, it's that the internet hits are independent and the probability of a sale remains constant. Those are the two conditions that we have to have, and we do. Okay, then part C says, hey, let's approximate this with the Poisson approximation. And to do that, we need to calculate one thing, and that is the mean, the mu. And you have to remember that the mean of a binomial distribution is simply n times p, or in this case, 2,500 times 0.001, or 2.5. So our average is 2.5, which makes sense, right? I mean, if we have 2,500 hits per day and we get 1 sale for every 1,000 hits, then you take 2,500 and divide it by 1,000, and that's 2.5 sales per day. That's an average, right? You obviously can't have 2.5 sales. It just means that's your average. So to do that, we have to go use the code with the Poisson, right? And again, we have to figure out, are we doing a PDF for exactly something or a CDF for a cumulative something? And we're doing a CDF, right? Because the question was, we're answering the same question, right? Use this approximation to compute the probability that the firm will have more than 5 sales. So we're doing the exact same thing where it's more than 5 sales. So we have to do 1 minus the CDF. So we're going to do 1 minus the CDF, where now in this case, N is the value of interest, so that's 5 sales. M is the mean, in this case 2.5. And now if we run this, oops. There's our answer. Pretty damn close to what we got before. So part D says, you know, how is the Poisson approximation? Well, it's pretty darn good. They're really, really similar. And that's it. We've gone through all the homework. Any questions?
Thank you.
You are more than welcome.
Yes, thank you. I do have a question about, and this class is reminding me that the study of statistics is so wide and vast. How, in your understanding, and do you teach the 810, the math 810?
I do not.
You do not, okay.
I do not.
Do you know how is it similar or different to this?
I unfortunately do not, because I've never taught it.
Okay, okay. No, I appreciate
I would imagine it should be pretty similar, because, you know, they're supposed to, one is supposed to basically grow out of the other. So I would hope that 810 would be pretty darn similar.
Okay. No, I just found it to be a different experience, you know, like reading through the research articles. You know, obviously doing the statistics is one thing, but then trying to understand what it is that you're doing is almost, you know, a beast in and of itself.
Yes.
And understanding, those are some pretty crazy nuances there. So I just didn't know which angle, you know, if it continued or on one or the other of those. But
Yeah, I would imagine 810 is probably focusing more on getting you guys to be able to compute more advanced statistical things, because we really only do very basic statistics in this course.
okay.
Very, very basic stuff. So I would imagine in 810, they probably get into stuff like chi-square analyses and ANOVAs and linear regression, the types of things that you would most likely have to do in your dissertations, because that's really the main point of 807 and 810, is to make sure that you are all prepared with enough statistical skills to be able to run the statistical analyses necessary in your dissertations.
Okay. Thank you.
So that's what I'd imagine 810 is probably about.
Okay.
All right, great class, everybody. I'll post the link to the recording when it pops up later tonight, and I'll see you all next week.
Thank you.
Yep.
Thank you.
Yep.
Thank you.
Good night.
All right, let me check.
All right, Cheryl, what do you
Cool.
want to discuss?
All right, so I was looking at the final project.
Yep.
And oh, I just lost it. The part one, I probably would have gotten farther if I hadn't got stuck on the first one. The first question about using the information provided in the data set. Describe each probability distribution and use histograms and numerical summaries. So that means, am I doing the five statistic?
5-number summary?
Yes, the 5-number summary on the freights probability, families per parish probability, and the number in family probability.
Correct.
Are those my variables? Okay.
Yeah, so you want to run histograms on all three,
Okay.
and then do the 5-number summary along with mean and standard deviation for all three. And then based on both the histogram and the numerical summaries, you should be able to interpret the data and say, you know, this one's fairly normal, this one's skewed left, this one's skewed right, you know, those kind of things.
Okay, yes. So I did that on the probabilities data set, not the families per parish, but the families per parish probability. So I will do that for the families per parish probability, freights probability, and number and probability. So that brings about the second question. Estimate the average cost. So I ran the program for the mean for freights.
Correct.
And I got 3.116 times 2,000, but I had to assume that I was buying for an adult.
Uh-huh.
Because I didn't know, it didn't give me how many in that, out of the family, like the mean 3.5, it didn't give me a mean for kids and a mean for adults. Do you know what